Okay, here we go. X coordinate at the current value of x. All together. And I said this was f, so the y coordinate. Okay, so then if we have an interval width of h, that makes our x coordinate on the right side of the interval. And its corresponding y coordinate. And we want what about that blue line? We want its rate of change, right? We know how much of a quantity that we have, or we know how much accumulation we have. We want to know how fast it's changing. And so how do we compute how fast it's changing using those 2 points? So rate of change. What's our general structure of rate of change? The general structure is change in y, change in x, which we know is h, right? And so change in y is? Final y minus initial y, change in y. What is it? It's the same change in y that the function realizes in that interval. Do you see that? It's the same, that change in y, it's this exact same change in y that the function realizes in this interval starting at x. Yeah. Okay, yeah. Okay, so do you see that though? That we're getting that change in y of the blue secant line because it's the same as the change in y of the function, right? We know what the change in y of the function is. We can use the coordinates of the points on the function. So for the same change in y as the function is our change in y of our secant line divided by? Which is? Just the change in x is h. Okay? So this, using the sliding interval, we said last time, you looked over the weekend, the sliding interval is much, much more compact, convenient, easy to work with than the version that was the literal version of the reverse process that involved left of x. That locks things up for us. Having all the left x in there kind of locks up this and doesn't give us the freedom we need to work with a nice expression like this, okay? So we're going to stick with a sliding interval from here on out. Sliding interval gives us this rate of change function. So there it is. Okay, and so again, is this an exact rate of change function or approximate? Those values of rate of change, are they too low or too high? For this example, too low, right? Too low because the actual rate of change is heading up faster, right, than the blue line, always. So if I were to make h smaller, we'd get a better and better approximate rate each time. So I'm going to make h a little smaller. Ready? So when I make h smaller, all those y values get closer to the actual rate of change. I'll do it again. And so now if you look at the difference, or the function and the rate of change function, there's like no daylight between them. We've got a pretty good approximation now, but we can do even better. Right? Super small interval now. So you can't even see, it's like the points are so close together, and so then that approximate rate of change is very close to the exact rate of change. And here is h of 0.005. So this is pretty close to the actual rate. So we're going to use this expression to mean both approximate rate of change and exact rate of change. How do we know which one it is? So we're going to use this expression, we're going to use this both to mean approximate rate of change and exact rate of change. It's just a matter of the value of h, right? If h is sufficiently small enough, so we might argue that 0.005 is small enough here, because if you look at, if we zoom in on what's going on here, right here, so you can see the interval now, but look at what's shown as the rate of change of our black function and our blue line. You can't, they're just pretty much coinciding, right? Coinciding. That's a good argument to say, look, this is the exact rate of change function. H is sufficiently small enough. Now we've got exact rate of change. Okay, so anybody have a question? So we looked at the same kind of example, but for the volume of a sphere. So we had the volume of a sphere last time. And what was that rate function? That rate function was, or the volume of a sphere was 4/3 pi x cubed, right? 4/3. And we said that could be accumulation. It could be amount, just the amount of volume, or it could be, we think of that as accumulated amounts of volume of a sphere, right? So as the radius changed from 0 to x, that will accumulate changes in volume up to 4/3 pi x cubed. Approximate rate function. Approximate rate function, remember we looked at for 0.55, we found the approximate rate for this value of h at x equals 0.55. And we found that we zoomed in and got an estimate for the exact rate, and we saw they were much different. Here, our approximate rate is always greater than the exact rate. See that? The blue line is showing more of an increase than what's actually happening at the current value of x. Okay, so what do? Again, we look at smaller and smaller values of h. And again, when h is 0.005, now that rate function is now certainly very much closer to what we found as the exact rate for that particular value. So this is now, we can just consider, this is the exact rate of change function. Meaning that h is sufficiently small. We use this notation. H is essentially 0. H is essentially 0. And this is the key to that. It gives us the rate of change at any current value of x for any width of a sliding interval, and when that sliding interval is sufficiently small, we get the exact, yeah, John?
Okay, when you have like a larger interval, like at the end of it, the secant line is like less than the rate of change of the exact function. So are we only looking at like the beginning value of x in there?
Yeah, so we use the rate. So here's 0.6. We use this rate that we calculate, the secant line, to be the rate of change at x equals 0.6.
So the second point in the interval, like we ignore that, right?
Well, no, we use it to get the rate. But so yeah, so we assign the rate, the rate of change according to that blue line to the starting value of the interval. And so then we only get one rate per interval.
Yeah, so if you zoom in on like the second point, wouldn't the blue line be actually like less than?
Yes. But if the current value of x is that, then the interval's over here.
Yeah.
Yeah, so yes, we're taking that rate and assigning it to the left side of the interval. The current value of x is always the left side of the interval. So we're going to take that rate that we get from those 2 points, and we assign it to the current value of x, and that's what we're graphing over there. Yep. Okay, other questions? So let's take a closer look. So what is our goal? Our goal is to get what we're calling a closed form expression. A closed form expression is one where I can just put in, say, x equals 0.6, and it'll, like, really fast, automatically generate that rate of change for 0.6. And let's take a moment. Let's go back to this point, which we, no, this is not exact. We want exact. So at 0.55, we came up with an exact rate of 3.7. So we'll call it 3.7. And so we want to review what this means. 0.55, comma, 3.7 is a point on our rate of change function where we're talking about the volume of a sphere. F is the volume of a sphere. This is its rate of change function. Here is a point on that rate of change function, 0.55 and 3.7. What does that mean? What do these numbers mean? So yes, 3.7 is the rate of change when x is 0.55. But what does that mean? Take a minute to talk to the person next to you. What does it mean that at 0.55 we get the value 3.7? Go. So what I mean is 0.55 what? 3.7 what? Okay? Yes, okay, good. So let's say we'll make our sphere in centimeters, right? So radius in centimeters, which means volumes in centimeters cubed. Go. Here's a hint. 3.7 is like a value of m that we've talked about in the past. 3.7 is like a value of m that we've talked about in the past. Okay, so we worked hard on this, but it's been a while. Anyone think they can interpret this point, 0.55 and 3.7, beyond just 3.7 is the rate of change? Yes?
When the radius is 0.55 centimeters, the volume of the sphere is growing by 0.7 cubic centimeters.
Okay, so when the radius is 0.55 centimeters, the volume is growing by 3.7 centimeters cubed. Per centimeter.
Which I guess is square centimeters.
Okay? Yes, sir?
At the moment, x equals 0.55 centimeters. A change in volume 3.7 times greater than a change in side length. And radius, my bad. Sorry. Any change in centimeters.
What'd you say? At the moment?
At the moment, x equals 0.55 centimeters. So the radius, yeah. The change in volume will be 3.7 times greater than any change in radius.
Remember this? We need one more little part to it. One more. What else do we have to include here? Yeah?
As the radius is changing or growing or increasing?
Okay. Yeah, that's kind of implied. That's true. That's true. We don't necessarily need to put that in, though. That's true. What else do we need for this to be true? The change in volume will be 3.7 times the. What about this change in radius? Any change in radius? What's that? Okay, and what about the moment? Yeah, we gotta say that this change in radius has to be really small, right? Because if we're talking about exact rate of change, if h is too large, then we don't have exact rate of change. So we want to qualify. So times the change in radius. I'm just going with what you wrote. So which is very small. Okay, so yeah, interpretation of rate of change means that the change in y, or in this case the change in volume, will be 3.7 times the change in radius, which is a very small change in radius, okay? So how about for a very small change? Okay, what is the units on that? 3.7. So centimeters cubed per centimeter. Do we want to make that centimeter squared? Does that mean centimeter squared? No, so a rate of change means that two things are changing together. If you change it to centimeters squared, then you're talking about 3.7 what? What is that? 3.7 centimeters squared is indicating what kind of thing? Area. An amount of area. We don't want an amount of area. We want rate of change, meaning for any change in radius, the change in volume will be 3.7 times that change in radius. Right? It's how much the volume is going to change for a small change in the radius. So we want to keep it as centimeters cubed per centimeter to show that these two quantities are changing together, and it's how fast the volume is changing with respect to centimeters. So just later on here, get it? So here's 0.8. 0.8 and 8.1. 0.8 and 8.1 is another point on the rate of change function. How is the volume changing now compared to how it was changing before? So here's another point on the rate of change function, 0.8, 8.1. Interpret it. Go. Practice. What's that? You must have passed out there for about 30 seconds or a minute. I talked much about that. That would be an area then. It would just be an amount of area. Is that what that is? 2.7 an amount of area? But it's a rate of change. It's not an area. So if you do that, then you're expressing just an amount of area. But this is a rate of change. This is how much a volume changes with respect to. So it's not an area. So if you do that, you're just indicating area, which is no, that's not right. Okay, so what's the rate of change now compared to before? How's the volume increasing for a small change in x now compared to before when the radius was 0.55? Faster or slower? Yeah, it's faster. So for a change in x now, your volume changes 8.1 times as much as that small change in radius. Okay? So this function is giving us the rate of change in centimeters cubed per centimeter at any value of radius. Any value of radius. So it's these numbers, these y values on this rate of change function are not a simple, straightforward thing. Accumulation and amount are much more simple and straightforward. It's just how much you have or how much has accumulated. Rate of change is a complicated kind of beast, okay? And we have to understand that. What is it? It's telling you how fast this y is changing, this volume is changing as x is changing. And it's a number for that. It's a number that's telling us how fast the volume is changing for a change in radius. Okay? Okay. Let's talk algebra. Oh no, you're supposed to say, oh yes, I've been waiting for this, not groaning. Okay, so here's our rate of change function. Here's our rate of change function. And we said that the original function was 4/3 pi r cubed, which is the volume of a sphere. So we can apply, this is the rule of the function, right? Remember that? This is the rule of the function. So now that we have a rule of the function, we can apply this function notation, we can apply the rule to that. So what does this rule say? This rule says, it says cube the input and then multiply the results by 4/3 pi. Do you see that? That's what this rule says. It says cube the input, whatever your value of your independent is, cube it, and then multiply by 4/3 pi, and that'll give you the corresponding value of the dependent. So we look up here, and we're going to do that. So what is the value of the independent here? What's the value of the independent in this expression right here? X plus h. So f of x plus h is we're just going to follow that rule, which says cube that input and multiply the result by 4/3 pi. So what will it be? Cube it, cube the independent value, multiply by 4/3 pi. Right? So we're going to cube it and multiply by 4/3 pi. That's what f of x plus h is in this case. Take the x plus h and cube it, and then multiply by 4/3 pi. That's what the rule is telling us. What about f of x? Again, what's our independent value? X. So what are we going to do to it? First, cube it, and then multiply by 4/3 pi. Okay, and so then the rate function says subtract those. That's our change in y, right? That's our change in y, and divide by the change in x. So here's that rate function in the particular case of the volume of a function. F of x plus h minus f of x over h. Okay, so this is something we could work on and simplify. And so for the volume, the rate of change of volume, we can get a simpler version of this. And I want to show you how graphing calculator can help with that. Let's see. Okay, so there's the expression, right? So we've applied the rule 4/3 pi x cubed to this expression, and that's what we got, right? 4/3 pi x plus h cubed minus 4/3 pi x cubed over h. So I'm going to take that, and I'm going to copy it and paste it so I can work on it. So this is kind of slick. Graphing calculator can do some algebra for you. So watch, I'm going to take this right here, highlight that, and if I go to math, I can go to expand. And it just did it for me. Just expanded that. Okay, and then I can grab this right here and just see how the hand showed up. So now if I take this and no, that was too much. It just moved it inside. So let me move it out again so you can see what happened. So here it is outside, and so I'm going to distribute it into here. So I'm just going to take it and lift it over, and it distributes it into all those terms. Okay? All right. And then I'm going to, so notice what happened. So I expanded out that first part, and then I distributed in the 4/5/3. So look at all those terms and you see what happens. I've got a 4 pi over 3 x cubed here. But that's exactly what I'm subtracting here, f of x. So what's going to happen to those two? They're going to go away. All right, so because that minus that's just going to be 0. So now I can use math. I can use simplify. And they're gone. So those, the first and the last, subtracted to 0. Okay, what now? So now with that first and last term subtracting to 0, notice that now we have an h in every term up there. So I'm going to look at this. I'm going to highlight that h, and the hand shows up, and I'm going to pull it over here to the left, and it's going to factor it out. So you need to have an h in every term. That's the goal, and you factor it out. And so now h over h is?
1.
Well said. They kill each other. So I'm going to simplify. Again, simplify. And I get this. So now we've come to a point where we really can't do any more. So what do? We started by expanding this x plus h cubed. And then we saw simplification, that we got the exact same term as this here, and so those subtracted away. Then we saw an h in every one of the remaining terms. So we could factor out the h, and h over h is 1. And then we're left with these 3 terms. And so what does this equal? This still is, we've done all valid work, so it's still equal to, we haven't broken any rules. We've done all. So these 3 terms now added together are still equal to our rate of change function. Is that the 3 terms added together? Is it exact rate or approximate rate of change? I heard exact. Is it exact rate or approximate rate? Those 3 terms. If h is close to 0, it depends. It depends on h. It's both. If h is relatively large or not small, then it's approximate rate. If h is sufficiently small, that's our exact rate. It works the same way as our this quotient here that we came up with, the f of x plus h minus f of x over h, because they're equal. So now, let's go back. So what did we find? So that is our R of S function, and we found that it's equal to this: 4 pi x squared plus 4 pi hx plus 4 pi h squared over 3. So how do we make it exact? If we want it to be exact, then we need h really small, or h, so for h essentially 0, really small, it equals, what does that equal when h is really small? It doesn't care what h is. It doesn't have anything to do with h. It just stays the same. What about this when h is essentially the same as 0? 0. And what about this? 0. So we have arrived at a closed form for the rate of change function for the volume of a sphere. This is closed form. We can stick in an x and it just cranks out the rate of change. And this is it's equal to that. It's equal to our rate of change function for a small h and that rule, 4/3 pi r cubed. So this is what we call a closed form. Rapid fire results. Crank in lots of x's, it cranks out lots of rates really fast. X is 1, crank out the rate. X is 10, crank out the rate. This is what we call a closed form expressions. It's the ones you've been dealing with your whole math career until you got to integrals. Integral was probably your first open form expression. Closed form, rapid fire results. common functions, common forms of functions that crank out values. In this case, rate of change values. So if we graph y equals 4 pi x squared on our GC file here, wrong one, this one. If I plot y equals 4 pi x squared, what should I get? We'll do it in purple. If I do y equals 4 pi x squared, and I graph that, it's exactly the same as what we got for our rate of change function with a really small h, so that they're basically on top of each other. So if I take it off, let's do red and blue, how about? So if I take it off, there's the blue one that we got from f of x plus h minus f of x for a really small h. And then if I put it back on, same function, but now we've got it in closed form, 4 pi x squared. Is there a question up here? Yeah, so we're going to do a couple of those, yeah. Yep. What? Yes. Yeah. Other questions? So, same function as this with a sufficiently small h. So what do we do? 0.55. So 4 times pi, we did 0.55 x squared. What is it? 3.8. Exact rate of change. We got 3.7. So this is truly exact rate of change at the moment that the radius is 0.55. 3.8 centimeter cubed per centimeter. Okay, so let's do another example. Any questions on the volume example? So we use this algebraic approach to reinforce what we already had got in terms of the function. But now it's a cleaner, closed form function. So let's do it for another example here. Where's my keynote? All right. So let's summarize here. So here's the notation for the rate of change function. F is any function. This is going to be our notation for the rate of change of f. The function whose values give the rate of change of f with respect to x. And we know that this is what it is. Exact or approximate rate of change? Both. Depends on h. Both. We're going to say this is flexible notation. If for non-small h, it's approximate rate. For really small h, exact rate of change. Okay, so let's go back to our square function. F of x is x squared. What is f's rate of change function? What is f's rate of change function? So whenever we ask for rate of change function, we're always going to start with the same thing. We're going to start with our form of the rate of change function, which is, this is how, whenever we want to find a rate of change function, we're always going to start with this. Well, in the next week or two. We're always going to start with change in y over change in x, or h. That's right. And now we have our particular function. This one gives the area of a square. So we're going to apply that rule to this expression. And what does this rule say to do? What does this rule say to do? It says square the input. That's it. So we look at function notation, f of x plus h. What's the input? It's x plus h. So the function tells us to square the input. That's what the rule says. Square the input. So we're going to do it. Square the input. And then f of x, square the input. Okay, so now you do by hand what I did on GC. You're going to expand. You're looking for simplifications in the numerator, and we're looking to factor out an h in the top. Ultimately, factor out an h in the top so we can have h over h be 1. Go. So now by hand, algebra by hand, to simplify the rate of change function for the square function f. Go. Everyone's writing. Everyone's writing. For these polynomials, that will always be the idea. That the first term will subtract with the last, and then you'll have h's, you'll factor out the h. It would be different for non-polynomials, it'll be different. Did you get 2x plus h?
Yes.
What is that? What does that mean? What does the expression 2x plus h mean? Volunteer. So what is 2x plus h? John. Of what? What is it? Okay, so somebody, so yes, somebody, so what is 2x plus h? Are you going to do it?
I was just going to say for any input x, it gives you the rate of change.
Right, exactly. It's the rate of change function. It is equal, for the square function x squares, it is equal to that. It is the rate of change function. Exact or approximate? Depends on the h. We want exact, so what do? We could do this. We could say essentially equal to what when h is small? 2x for h essentially 0. So we just got the closed form for the rate of change. Of a square function. So what is Rf of 7? What's Rf of 7? 14, which gives us the point 714. What does it mean? Tell the person next to you. What is 7, the ordered pair 714? Interpret it. What does it mean? Okay, what is the what does the point 714 mean? Somebody new. Volunteer. What does the point 714 mean? You have it back there? Yeah. In the reddish shirt, yeah. Yeah. Yes, you. What did you say 714 means?
At the moment, the rate of change is
Okay. So at the moment, and what does the 7 represent? When you say at the moment 7, what is 7? What is it? Yeah, what is the x value here? Side length. So when the side length 7, the rate of change is 14. What's the units on it? 14 what? What are the units? So I didn't really give you, so we could go back to centimeters again. If it were centimeters, what would the units on the 14 be? Somebody knew. What were the units on the, yes sir? Centimeters squared per centimeter. So it'd be 14 centimeters squared per centimeter. And what does that mean? What is that rate of change? 14 centimeters squared per centimeter. Somebody knew. It means that. Yeah, Hector.
At the moment of the side length 7
Okay.
centimeters,
Uh-huh.
the change in area is 14 times the change in side length for a very small change in side length.
Okay. Yeah, so for a very small change in side length, close to 7, we expect the area to change, what? 14 times as much as whatever we pick for that change in side length. Okay, so if you understand what those words mean, then you should be able to do this. If you understand what those words that he just read and I just said mean, you should be able to estimate, use that fact to estimate f of 7.03. Who can do it? Who can do it? Estimate f of 7.03 using the fact that the rate of change is 14 when x equals 7. Everyone got it? It's quieting down. Everyone's got it? If you don't have it, you're getting help. If you don't have it, you're getting help. Morgan and Cerny, can you help them with this task? It got quiet, which I don't think meant everyone got it. I think the opposite. So get help. If you don't, get some help if you need. Which is what? What's the area at 7? Good. That was good. Someone's got it up here. Okay, so when the side length's close to 7, we're literally applying this definition of rate of change. We're saying for a small change in side length near x equals 7, the area changes 14 times as much as that change in side length. So if we truly understand what that's saying, then we could make sense of this f of 7.03 and get an estimate for it. So somebody new thinks they got it. Somebody new who hasn't spoke up today. Yes, ma'am.
F of 7.3 is about 49.42.
Okay, so process, not answer. So focus is always process, not answers.
So take the change in x. So it's 7.03 minus 7.
Okay, so do we have a little change around 7? What is the little change? 0.03. And she said 7.03 minus 7. So we have a little change in x, okay?
Use that change in x, multiply it by the rate of change at the moment when x is 7
To get?
to get the change in y.
Okay.
So that is 42, or 0.42.
Here's the crux of the meaning of the rate of change. Any change in x, the change in area will be 14 times as much as the change in x. There it is. And you got 0.42?
Yes.
So 0.42 is, tell me the meaning of that number again. 0.42 is?
The change in y. So then you take that and add it to f of 7, which is 49.
So f.03 is approximately equal to?
Is approximately equal to f of 7 plus
Starting y, or starting area, plus
the change in y.
the change in area.
It's about 49.42.
How many people, before we started doing it together here, how many people had gotten that before we started together? Okay.
No.
Okay, what are the units on that? What are the units on 49.42? Centimeters squared. Per centimeter? No, this is an approximate amounts now, final amounts of area. So we got a change of x of 0.03, which by the constant rate 14 gave us a change in area of 0.42, and then starting value of area plus the change in area gives us this. This is an approximation now. Approximation. What's the actual area? Actual area would be 7.03 squared. Anyone do that? What's that? 49 point what? Nice and loud. 42 what? Okay, so very good approximation. That's approximating the actual area at 7.03.